All right, I think we're live. Hey, everybody, welcome in. We're live. Thanks for joining us. We're going to be talking about GPUs and stuff. I'm here with Daniele. I'm going to do a quick introduction because we got a lot to get through, right? A lot to get through. So we're going to have some
slides.
Yeah, 100 slides. So we're going to have a presentation, and then if you would like, post questions in the chat, and we'll get to the questions after the presentation. Just because, like I said, we got a lot to get through. Yeah, post questions in there, and then I'll try to answer some stuff too in the chat while I'm in here in the background while Daniele is presenting. But let's go ahead and get started, Daniele. I'll go ahead and add your stuff there. But let me introduce you to. Who are you? What do you do? Or what's Learn Cube?
So I am one of the instructors that learn Kubernetes. So I teach Kubernetes, and I spent my last few months learning GPUs. So I think today we're going to dive into how do they actually work and how do we use them in Kubernetes. So I think that is the plan.
Awesome.
Let me just say that when I started this project, I thought GPU would be just like any other resource in Kubernetes. I was so naive. Because things are just so much different. So that is the plan for today. We're going to see why they're so different and how we use them.
I agree. All right, so let me add this. All right, we're going live on Twitter again too. I changed the one over there. Okay, so cool. So we're live, everybody. We're live everywhere now. We're good to go. I'm gonna go ahead and hide. I'm gonna listen. I'm gonna come up with some questions too, just in case we don't get a ton of questions. And let's go and get started, Daniele.
Okay, cool. So if you have any questions, as Mike said, just write them down. I will get to them at the end of the presentation. For now, I will focus on the content and trying to explain how this GPU works. So my name is Daniele. People call me Daniele, Dan, D5E, to make a joke on Kubernetes. And I had the pleasure to present at KubeCon 3 times. And I was one of the first 500 engineers to obtain the CKA in 2017 when the exam was 3 hours long. So long time ago. And I teach Kubernetes. That's what I do for my day-to-day job. And today, and not long ago, we published a book with Siam on GPUs and Kubernetes. And I learned a lot. At the beginning of this journey, I was quite naive, like I said, and writing these books and just exploring the area just gave me some insights that I thought I could share with the rest of the community. So here I am today. So to understand what we're going to talk about today, we need to take a step back and understand what is that we are doing with applications that we deploy in Kubernetes. And even before Kubernetes, we need to understand how applications are deployed on Linux and the Linux kernel. Then generally what you do, you write an application. That applications needs to interact with the network, or maybe needs to read some file from disk, or needs to use some CPU. So all of these different sort of tasks that needs to be completed. The application is not aware of what kind of hard drive you use. It doesn't care. It doesn't know if it is an NVMe, an SSD, and a normal hard drive. So what does it do? It basically asks for files from the Linux kernel. So the Linux kernel works as an API, and then we call these API system calls. Now, it turns out that everything that the application does needs to go through these API, which is offered and exposed by the kernel. And throughout the years, then people started wondering, can we actually do something with these API calls? Can we actually group them? And this is a map of all these different API calls you could have in the kernel. And the idea is yes, we can actually group these API calls and also set sort of limits on how those API calls interact with the kernel. So one of these ideas was control groups, and the idea is very simple. We said, okay, what if I can limit the amount of resources that can be accessed through the kernel? In the same way that you design an API, an HTTP API, and you say, I want to set some rate limiting on the number of calls that can be made to that API. This concept is sort of similar for the Linux kernel. We don't limit the number of the system calls, but we limit how much memory you can use, or how much CPU or or for example, the bandwidth for your network. So control groups are a way to define resources that can be consumed by a group of processes. And you can create as many as you want, and each control group can contain a different set of processes. It doesn't have to be only one, can be multiples. Now, control groups are good, but there is something else that there is in the Linux kernel that we use quite often when it comes to container, and that's namespaces. So namespaces is a way to basically segregate the process and make sure that it has its own view of the world. So, for example, one of the namespaces that we have in the Linux kernel is the mount namespace, and the mount namespace is basically just a way for the Linux kernel to isolate access to the file system. So, in this particular case, I've got a Node.js app and I've got a mount namespace. So, you have a JVM app and I've got a mount namespace, and it's basically having a completely isolated view of the current file system. However, the reality is that we just created a folder and pretended that that was like the full hard drive. So I can create multiple mount namespaces and they all get their isolated file system, but in reality, they're basically just subfolders inside the main file system. Now, this gives me an isolated view, so the Node.js or the JVM app, they can interact with the file system as they could edit any of the files and folders there. Now, namespaces, we don't have just the mount namespace, we have the user namespace, the ID namespace, and they're all designed to isolate different parts of the process and how we can interact with the host on the Linux kernel. But the idea is that these C groups and namespaces are quite low level, so very it's not easy to deal with them. So the idea is that what if we build some abstractions that let us interact more easily with these sort of constraints that we set on processes? And that's basically the idea behind Docker. We just mix these control groups and namespaces, and we end up with something like a container engine like Docker. Of course, there are multiple ways to skin this. There are multiple tools that offer the same sort of functionality. You might have heard of Containerd, Cryo. But the idea is that they all come down to, okay, how do I set those limits with control groups? How do I create isolations with namespaces? Now, this is good. This is basically where we're dealing with the Linux kernel inside. We're dealing with the Linux kernel. And the other things that we need to have a look at is something which is quite obvious. So if I show you this, you will probably say, well, Daniele, why do you have this slide? And bear with me for a second. But CPU, so we have the Linux kernel, we have a CPU, and a CPU, like the hardware, can only execute one instruction at a time. However, you might be, browsing the internet, having a spreadsheet, having Word open, typing something on a chat, and you're using multiple applications at once, and they are all working simultaneously. So how does it work? Well, the reality is that the hardware can only do one thing at a time. But what if we actually slice this computation and we actually interleave them? So we have a few microseconds for the first one, then the second one, then the first one, and we go back and forth. Then if we give each of those applications a unit of time and we slice it, then it almost appears that the applications are working at the same time. So they are working simultaneously. Now, this is quite normal, and you experience that all the time, and we are so accustomed by it that we actually don't even notice, right? But this is how it works. And if you have two cores, the same things happen over multiple cores inside your CPU. The other things which happens quite a lot, so we said that the hardware, the CPU, can only execute one instruction at a time. So how do we actually switch between processes? Well, the way it works is that the CPU will have some registry, some state that needs to be, which is used to execute the instructions for this particular process. So if we need to switch from one process to the other, what happens is we need to save the state for this process, load the state for the next process, and then continue the execution. And then if we need to go back when we do the switch, then we need to do the opposite. So it turns out that this is some extra task that we need to do in order to pretend that two processes can run at the same time. So we need to do this quite a lot, like very, very frequently, so the user can actually see two applications running simultaneously. But in reality, we are just saving states, loading states, doing execution, and then moving on to the next one very, very frequently. The other things that we do in the Linux, in the hardware, which we sort of give for granted, is how we allocate memory. And then the memory allocation actually works like this. You don't actually get access to the memory, your RAM, directly. Instead, what we have is inside the CPU, we have a component which is basically mapping virtual memory to actual physical memory in the RAM. And the reason why we have this is because you can give away a contiguous memory space, which is virtual, which is not necessarily mapped to a contiguous space in the RAM as well. It's also got other benefit, but in reality is that all of these problems are basically abstracted away from you, and you don't need to worry about how the pages are located inside the RAM. Everything is actually handled for you by the memory unit. Now, all of this is sort of granted, sort of like, we look at it and say, yeah, of course it works like that. It's always been, right? Why are we even discussing it? But it turns out that to understand GPUs, we actually need to understand CPUs first. And GPUs are very, very different from what we just experienced. And the first things that I want to show you is how actually this CPU works. So the first thing I want to show you is a kernel in the CPU. So we talked about the Linux kernel. And then when we talk about GPUs, there is something else also called the kernel. It turns out that the kernel in a GPU is basically just an operation which is done on some data. Now, I've got a program here. I've got some lines of code for Python code, and I want to show you how this actually works inside the GPU. First, I define some data. This data is actually defined in the program itself. So, and lives in your memory, in the CPU and in your memory, in the RAM. Now, every time when I create an array using this memory, these data is actually transferred from the memory I've got on my RAM to the memory inside the GPU. And then when I want to do any sort of computation, this computation is actually what we call the kernel. And the kernel will basically go through all of the data, and it will basically apply the transformation to get the result. Now, this result will be held into memory inside the GPU. So to get it back, you will need to transfer this memory from the GPU back to RAM. Okay, so this is already something interesting because we don't actually use the memory that we've got locally. We actually need to transfer this memory back and forth. So something to keep in mind. But the other things that we need to keep in mind is that these kernels, so in this case, I'm creating two arrays. So both instructions, CP array, will basically transfer the memory from my RAM, from my local RAM to the GPU. And then this addition between these two vectors will basically trigger a kernel. And the kernel will basically try to add all of these numbers together. Now, if I have a second kernel, this second kernel will basically execute again on the data that I've got previously. But there is a distinction between this and CPU. So when I ask a kernel to be executed on GPU, this will basically monopolize the GPU until the kernel runs to completion. So whereas with GPUs, what we do is we take slices, we pause processes, and then we resume them all the time. With GPU, what we do is we execute a kernel, and that kernel will basically block the execution for any other kernel that is going to be executed on GPU. This is basically for saying that the GPU can only execute one kernel at a time to completion. It cannot be stopped. So if you have a very long kernel like this one, then the green block will need to wait until it is done. If the kernel takes 30 seconds, then the entire GPU will be monopolized, will be busy for 30 seconds. Now, this is just one part of it. So we talked about GPU, we talked about transferring memory. So transferring memory and actually the code that goes executed in the GPU. So we saw these multiplications and additions and things such as the state for the GPU and a bunch of other things are actually all wrapped into what we call a CUDA context. And a CUDA context is basically just a way to describe that we are using, there is a program inside the CPU which is going to use the GPU, and it needs some data to be allocated. There are some operations that need to be executed, and there is some GPU state to keep track of. So this is usually what we call a context in when we deal with GPUs. And what you need to remember is that we always start from a normal CPU process. The CPU process will basically open a context on the GPU, will allocate the memory, and then at that point in time, then we will have kernel and execution. So if you have multiple processes, they will all need to do the same sort of operation on the GPU. Now, why are CPU and GPUs so different? Well, we talked about these CPUs switching tasks all the time, saving registries and then restoring them. And then they do that with quite a lot of frequency. Then the other things that we have is in all these CPUs, they are basically like the arithmetic logic unit. And those basically are the core components inside your CPU, which are basically doing the arithmetic additions, multiplications, and so on and so forth. But it turns out that those are so fast at executing code that there is a bunch of other silicon inside the CPU, which is dedicated to predicting what is going to be the next instruction. And if you think about it, when you write code, most of the time there are plenty of if-else, right? And you're not sure which branch your code is going to go to. That's why, but the CPU needs all of these instructions to actually execute them. So CPUs have developed some silicons which is dedicated to predicting what is going to be the next instruction, so they can basically feed all of these to these arithmetic logic units so they can crunch the numbers in advance. They are so fast they can do that. It turns out that there is a lot of logic inside the CPU which is designed to control and speed up this process of guessing what is going to be the next instruction. But for GPU, everything is so different. It is so different because basically the design of the hardware is different. We don't have if-else when we go with the GPU. With the GPU, we have like a massive matrix of data, and we just need to compute. For example, we have pixels, and we need to draw an image, and we just need to do some calculation on those pixels. We don't need to predict if it's going to be an if-else. No, there's going to be the same multiplication over and over for 64, 128 times, and so on and so forth. It turns out you can have one control logic unit for like 64 arithmetic logic units. So you can have like less silicon dedicated to deciding where the next instruction is going to be. But this has some consequences. So it has some consequences because the GPU is designed for predictable workloads, not like the CPU, which needs to deal with different, with branch prediction and stuff like that. So when you locate memory in the GPU, this memory is visible to the process. It sees the entire memory. Is a context is going to use 8 GB of memory, and another one wants to use the same GPU, then both will see the 16 GB of memory. This is really puzzling, right? But the other thing which is even more puzzling is that if you allocate 8 KB of memory inside the GPU, then what happens is the GPU will basically allocate 2 MB, because GPU will basically allocate a chunk of memory, will not just allocate one little bit of memory, what you need, it will basically allocate a chunk of memory that you can use. And the reason for this is speed and simplicity. So the GPU can basically just going to give a chunk back to you. And if you're going to use more than that, and it's within the chunk that you're given, then you're fine. But at a time where you want a very big chunk of memory, then what happens is the driver might allocate even a bigger one for you. But that's actually used but not exposed. So you really don't know how much memory has been allocated to the process. So here is an example. I've got I need 3 units of memory, but the allocator gave me 5. Then the driver reserves 5, but I'm sort of aware that only 3 are allocated. So there is no way for me to know how much is actually reserved by the driver, which is quite different from what we get from the CPU. And then, so to recap, in CPUs, we have hardware dedicated to controlling to predicting where the next instruction is going to be. We have cache, we have these branch predictors. But in the hardware for GPUs, then we just have execution unit. And that basically means that it's very hard to do context switching to the point that we don't actually do it. That's why the GPU can only execute one thing at a time, and you cannot stop it. It's because it's too expensive to actually have all of these save and restore things that we have got in the GPU. The other things that we have with CPU is we have granular allocation of memory with pages which are like 4K, and then we've got all of these extra silicon dedicated to mapping this memory. But in the GPU, what we do is we just allocate chunks. Very easy. It's imperfect. We don't know what is reserved, but it's much easier, and you can just give a chunk to what needs to be allocated and executed. With the GPU, we can stop and resume because we have all of these extra sort of ways to do it. But with GPUs, there is no stopping. You can only execute to completion, no stopping whatsoever. This is not something you can solve in software. This is actually by design in hardware. And that's why we cannot do it. We cannot work around it easily. And then in all of these CPUs, then generally, we interact with the Linux kernel. And in the Linux kernel, we have things like C groups, we have namespaces, we have the complete file scheduler. Whereas in GPUs, none of that is actually available to us because everything we do goes actually through a GPU driver. And that's also another big sort of point is that GPU, so Linux kernel is actually open source. And if you think about it, C group namespaces were all contributed incrementally, right? And new namespaces are added, and then there is a community which is actually developing on top of this, is developing the kernel. Whereas the driver, which is provided by the GPU, is a closed source blob that you have some API you can interact with, but you don't really know what's going inside. So these are the two differences. So we sort of talked about how the hardware is actually a limiting factor in GPU. Is also double-edged sword, I guess. It's not just limiting, but it's also so powerful because we took some different design choices when we talk about GPUs. But let's go, now we talked about the hardware, we talked about the Linux kernel, but how does this work in Kubernetes? Well, generally, in the context of just creating a pod and just creating an application, generally what we do is we assume, we send a request to the control plane and a pod is created. And then a pod is created through something called the container runtime interface. Good. But what about GPUs? Well, first of all, Kubernetes doesn't know where are the GPUs. It doesn't know that there is a GPU, and the container needs to be sort of relax some of the constraints to actually look at the GPU, which is mounted as // NVIDIA 0. Doesn't actually how to drive this GPU, and if there are multiple GPUs on the same node, how does it choose the right GPU node? There is no information about any of this in Kubernetes, so Kubernetes is basically not aware of what's going on. So there are basically 4 layers to solve this. There is the GPU itself, then there is the driver, which is basically just driving the GPU. Then there is the NVIDIA Container Toolkit, which is going to help us fix some of the issue with the container itself. And then there's going to be the NVIDIA device plugin, which is going to help us with the kubelet. So 4 components. let's have a look at how they work. So first we have the driver. So when you install the driver, this is actually installed with the Linux kernel as a driver itself. And what it is do, it basically expose the NVIDIA as something you can consume. First step. The second step is actually making the container aware of that file descriptor. And unfortunately, we don't have a container GPU interface. So what we do is we actually patch the container runtime interface. And the way we do the patching is basically through the OCI runtime. Then the OCI runtime is basically divided into, it's got hooks before the container starts. So after the container is restarted, but before the process starts, then what we do is we execute a hook, which is going to inject some environment variables and is going to relax some of the constraints with the container itself. So it's going to mount the dev NVIDIA, it's going to inject the libraries from the host and environment variables, and it's going to make sure that the device C groups is fine. So all of this process is actually done for you by the NVIDIA Container Toolkit, and this is basically the trick that NVIDIA is doing to actually make sure that you can actually mount the GPU inside your container. So I think it goes through several steps, but the idea that I want you to remember is that the container needs to talk to the GPU, and by default, the container is fully isolated. So we need to punch a hole in the container and just give the GPU access. The problem that we have is if we have multiple GPUs, which one we choose? And how do we make sure that the container knows which driver to use for that GPU? So all of this is basically solved by the NVIDIA Container Toolkit using the OCI runtime, using a pre-start hook. Now, on top of that, what we have is the device plugin. So the device plugin is basically something you can install, and it comes basically as a daemon set. And what does it do? It basically accesses the underlying node, and it can basically check the GPU itself. And what does it do? It registers itself with the kubelet. And it basically works as a broker. It's going to go and check the GPU and report the status back to the kubelet. So the kubelet doesn't actually know about GPUs, but with the device plugin, it is GPU aware. It's going to discover these GPUs and then send it back and tell, okay, I have a GPU. So this node is GPU ready. So how does this work in Kubernetes? So when you create a node, when you create a pod, which is got, something like it's got a request for a GPU, what will happen next is same as usual. The container, the specification will go in control plane. It will be stored in etcd. The controller manager will go and create the pod. The pod will be added to the scheduler's queue. The scheduler will go through the usual phase, which is filtering phase, scoring phase, and then binding. So filtering and scoring. So filtering will basically do, okay, which nodes have GPUs? Okay, and from this, and this is the first part, which is the filtering phase. Then we've got a scoring phase, which is basically going to say, okay, which node is the best node? Can we rank those nodes and figure out which one should go to? Probably the empty one is the best one. So it's going to score, and at the end of this phase, we will do the binding. The binding will basically link this pod to a particular node. And at the end of it, then the kubelet will be able to finally place this pod on that node. And this is where the device plugin plus toolkit plus driver work in concert. And the idea is that as soon as this pod is deployed there, then the kubelet will say, okay, can we allocate one GPU for this pod? Then the device plugin will basically go and start this. Will basically interact with container runtime. So containerd, it will go through this phase of actually starting the container, patching the container, injecting environment variables, and then inside it will basically just start the container with the driver, so they can basically use this file descriptor and drive the GPU. So this means that at the end of this process, your container is running, and even if it doesn't have any driver for the GPU, can still use the GPU because the driver has been injected dynamically. So at the end of this, you have a running pod with GPU. And this is also the end of my talk. So I know it's a lot to take in, and there are several phases on how this works. So all of these, of course, you can find it also in the book that I wrote with IAM. So we dive quite in details about all of these processes and how these containerd prehook, for example, are called, and what kind of values are actually injected there. But I think if there is something to take away from this talk and the time today, is that GPUs are different. GPU are different because the design of the hardware is different. And then sometimes we are so accustomed to thinking CPU that we forget. We give things for granted. And I think that was my error. And a better way to approach this is to basically think about how the hardware for the GPU is designed, and what kind of limitation is actually what kind of limitation advantages is designed for. Then we had a look at this Linux kernel versus GPU driver. So all of these CUDA contexts, these allocations, these kernels, they actually go through. They don't go through the Linux. They go through the Linux kernel, but eventually everything driving this is the driver from the GPU, which basically means that whoever controls the GPU driver is in charge of doing things. So in this case, the Linux kernel takes a step back, which also means that we cannot use things such as C groups and namespaces, because they don't exist in the driver itself, since the driver is doing all of these computations. Can those be added? Well, only if whoever is writing the driver is going to add them in. So you will need to go and ask the NVIDIA if they can do that. And I don't think this is something that they designed for. The other things which for me was like very surprising is that most of the design for Kubernetes sort of assumes the Linux kernel and assumes C groups and namespaces and assume containers, but it's actually, when you look at GPUs, they actually feel like they're second-class citizens, because you've got like this different way to drive them and different way to interact them, and all of the power actually goes through the driver. It doesn't go through the Linux kernel. So all the things that we use with the Linux kernel, like CPU slicing, a complete file scheduler, is actually not useful because it's not applied to GPU. So it looks like, okay, this GPU is like it's like something completely different, which doesn't fit in the current way of thinking of how we deploy containers. And then we had a look at these 4 layers. So I think this is where most of the confusion I find myself sort of confused on how these different layers interact. And I think it's really important to actually nail this down. Understand that we have a GPU at the bottom. There is a driver. Driver is not enough. We need to actually patch these containers to be GPU aware, to inject this environment, to inject these drivers. And we also need a way for Kubernetes to understand that there is a resource that can be used, and we need that device plugin to be that role. So I think those are like the main takeaway for me from just installing and running a GPU in Kubernetes. And this actually doesn't cover how we share GPUs, which is something I'm going to cover later on in December. But this is just basically the very, very basics on, yes, I've installed a GPU in Kubernetes and I can actually use it. So yeah, that's all I wanted to share with you today. So thank you very much for listening to my talk, and thank you very much, vCluster, for having me.
That was awesome. Yeah, that was awesome. Yeah, so join the next one if you want to know how to share GPUs.
Yes.
The basics, there's a couple of ways you can use a GPU with multiple applications, right? Like we'll say the name like MIG and then time slicing and stuff like that. But yeah, you're gonna get into that one in the next one, and then we've also got some other videos. Yeah. We had another question. Will the slides be posted somewhere that we can access?
I think most of the diagrams you see are also available in the book itself. So yeah. I think the book goes. I only had 30 minutes today. So
yep.
The book goes much more into detail. So I think I would suggest you actually go through the book. This is actually the first chapter. Yes, I expanded on some of the diagrams, but the book also goes more into the details about the code and configurations for the GPUs and why we have these configurations.
And I'll post the link to the book and stuff too in the YouTube video in case you want to see that. It's also in the chat and everything too. And then we have Salman saying, great insights by the legend, Daniel, as always. Yeah, it was a great presentation. I super enjoyed it. It's like I always pick up a little bit every time I watch these because I've watched a couple of presentations about like how GPUs work because they work so differently, and it's like I pick up a little bit here and there, but I have to keep watching them because I forget. Right? Like, it's like, oh yeah, it's a little bit different, right? Like this thing was made for video games.
It is so different. It is so different. Yeah, and I'm to be honest, I prepared this and I had to reread my own notes as well because we just give things for granted, and then you go GPU world and everything works in upside down, and I get lost so easily.
All right, well, awesome. Yeah, so that's what we got for you today. Join us for the next one. Links will be in the description here, and then we've got links everywhere else. And if you've already signed up for this one, you're probably gonna get an email about like the next one that's coming to on the 4th. But we'll see some people at KubeCon coming up soon, and then after you're done with KubeCon and you come talk to us at the booth, come back and watch the next webinar, download the ebook. I think we're going to have some book signings and stuff going on at the booth and everything too. So yeah, stop by, ask questions and all that too. But thank you so much, Daniele, for coming. Where are you presenting anywhere coming up soon, or are you going anywhere? You're not going to be in Atlanta, right? But you're going to be in Amsterdam?
Maybe, yes. Yeah, maybe. I think Amsterdam is more likely, I guess. Not Atlanta, not this time. Yeah, I think I'm just, to be honest, I'm looking forward to the next chapter. Gotcha. I think this one, chapter 1, so this was the fundamentals. I think this was by far my favorite. But next one, there is something else which I'm also very interested about, which is the Kai scheduler. Yeah. And then, I don't know how it's pronounced, but Hami? H-A... I think it's either Hami or Hami, right? Like it's one of them. Yeah. I don't know the right way to say it either. I still say like Ubuntu, and I hear people say like Ubuntu and stuff, so I don't know. Okay. Anyway, that one, I quite like. I think it's a very clever way to share GPUs. So I'm really looking forward to that. To be honest, we'll see. I've done a little bit with the Kai scheduler just to see like how it works and like how it like steals the GPU and then like you attach to it to do like fractional stuff. But I haven't done any of the really good custom scheduling or anything like that. All right, cool. Okay. Yeah, so that's what we got for everybody today. There wasn't a lot of other questions or anything like that. Join us at KubeCon. I posted information about like the events in there too. Join us for the event where we're going to be doing some stuff with NVIDIA, and click that, and we'll send out more information about that coming up soon too. But thank you so much, Daniele, and we'll see you next time. Thank you. See you. Everybody. Thanks for having me. Oh, do you have anything else you want to say before we head out or anything, or just join us next time? Very much so. Yes, I think that's pretty much it. All right, Thank you very much for having me. All right, everyone, have a good day, good evening, and everything else, and see you next time.